Welcome back. Picking up where we left off, in this lecture, we'll be talking about multidimensional histograms and how to use them. We'll start by explaining how 2D histograms work. Let's imagine the first two rows of a dataset contain the XY coordinates of different points. Then, we can use a two-dimensional histogram to get an idea of how the values are spread out across the plane. You can think about it as a histogram on top of a scatter plot. It's a good idea to have the matrix in front of us when we're trying to interpret the results, so we can call it right now. All right. So, the function which constructs a 2D histogram has a very intuitive name, histogram 2D. Let's call it and pass the first two rows of matrix A as arguments. For the sake of this example, we can conceptually assume the first line represents the x coordinates of the points, while the second line, the y coordinates. Before executing the cell, we can also set the bin size, so the output is more contained. We see a tuple consisting of a 2D array and two other 1D arrays. The 2D array is the density array here, while the other two are the bin edges for each plane. The first 1D array contains the bin edges for the first input variable, which contain the x coordinates. Similarly, the second 1D array contains the bin edges for the y coordinates. However, there is a slight twist when we look at the density array. The values we see in the first row of the density array include all points whose x value falls within the first bin. Therefore, if we imagine the xy plane, all the values in the first row of the density matrix will be about the first bin on the x-axis. Hence, the 2 we see in the third position suggests that there are 2 points which feature in the first bin on the x-axis and the third bin on the y-axis. Therefore, we're looking for points that have x-coordinates between 0 and 0.75 and y-coordinates between 5.5 and 7.25. Looking at matrix A, these are clearly the 2, 0, 6 points. The second row of the density matrix will represent all the points that have x-coordinates between 0.75 and 1.5. The ones appear in first and last place, meaning one of them has a y-coordinate between 2 and 3.75, while the other one between 7.25 and 9. If we look towards the original matrix A once again, we'll see that these are the 1, 3, and 1, 9 points. The last place we see a 1 in the density matrix is the first column of the last row. This means the x-coordinate will fall in the last bin, while the y-coordinate in the first. Hence, it's a point with an x-coordinate between 2.25 and 3, and a y-coordinate between 2 and 3.75. Clearly, this is the 3, 2 point, which was also the only one left. The 2D histogram might not be as easy to read, but it gives us a good idea of how density is distributed among the two axes. If we had input arrays of more than 5 values, we'd get a better idea of just how useful it is. So you can do that on your own as practice. Before we move on from histograms, we need to mention that there exist higher dimension ones as well. The function we use for them is called histogram dd and works similar to its 2D equivalent. If we pass the entire matrix, we'll see that the output consists of 4 matrices. Essentially, there's a 2D density array for each bin of the z-coordinate array. If it helps you visualize this better, you can imagine we're stacking the 4 density matrices to create a density tensor, which depicts the density in 3 dimensions. Whew! That was exhausting, right? After covering histograms, we've finally gone through all 4 parts of the statistics page in the NumPy documentation we examined in the beginning of the section. However, our work here isn't quite done. In the next lecture, we're going to look at how these functions handle incomplete arrays and what it means to have NaN equivalent functions. Thanks for watching.